But I guess Pravesh already introduced worst case, going beyond worst case, so he already motivated my talk really well. So we'll continue on that thread of trying to get guarantees beyond worst case. And here we'll kind of switch gears and talk about sequential prediction. And this is joint work with Steve Haneke, Shai Maran, and Abhishek Shetty. And I think the entire project was virtual. I think we've never met together in one shot ever for this project. Okay, so let me begin. So we know that a lot of decision making today is actually sequential. So you're not just making one decision and getting over with that model. You're making decisions one after the other. And these are some classical applications from self-driving, spam detection, medical diagnosis, to more recent LLM-powered chatbots where you're interacting with them one after the other. So a lot of decision making, we want algorithms to be doing well when they're interacting over multiple rounds with the system that we have. But unfortunately, this is not that these systems are really good. They're actually not very robust. And these are some articles that you probably all might have seen, how Tesla autopilot has crashed. There have been a lot of errors that have come on these systems when they do diagnosis in medical systems. And even more recently, like hacking of ChatGPT starting. And this one's my favorite example, which is, this is a New York Times article where the Apple Watch would just, for people who went skiing, would just activate that their heart is failing. And there would be 911 dispatchers sent. And this happened a lot of times with this distress call. And it was only because there was some spurious correlation with skiing and this system triggering. So all to say that these ML models, even though they're doing well most in distribution, they make costly errors on adversarial or auto-distribution data. So when they see something that's like not what they're expecting, they end up making a lot of mistakes. And these can be very costly in real life. So we want to kind of handle these settings. Now, generally what happens is that when we think about these two worlds, we can go to two extremes, like really far extremes, where we can think of all the interactions being completely stochastic or them being completely worst case. So what do I mean by that? When you think of stochastic data, you can think that data is drawn from some unknown fixed distribution at every round. So there's no adversary in the system. It's all IID data that you're getting. You could take a very, very pessimistic view and be like, OK, the world is really bad. All the data is generated by an adversary who knows everything about how you're going to operate and how you've made decisions before. And as could be obvious from these settings, it's very easy to get strong guarantees in the stochastic sequence because you have no adversary. But perhaps this is too simplistic to model real world. Whereas here, it's too pessimistic to get. I mean, you can get some guarantees, but they're really, really strong, really, really hard to get these guarantees. But of course, it's very robust to changes attacks. Like you're assuming worst case, so you're trying to be good against anything that could happen. I guess the motivation is that real world is kind of not worst case, but somewhere in between these two extremes. So you want to get results which are kind of keeping the best of both worlds, where you get strong guarantees, but you're also kind of robust to adversarial changes. So I'm going to try to motivate this problem. And the question that we're going to ask is, can we achieve strong guarantees while being robust to adversarial and out-of-distribution data? And the key idea here for the talk would be that we're going to try to predict with certainty. So whenever we make predictions, we're going to try to make these predictions be correct. And we're going to abstain or not predict on things that we think are not good. OK, so what is the motivation for this? That maybe not predicting in these cost-sensitive applications is better than making incorrect predictions, right? So like for medical diagnosis or self-driving cars, maybe better to give the driver the access than making a wrong decision, because this can be costly. And so today I'm going to talk about a framework that sort of allows for this abstention and interpolates between this purely stochastic and fully adversarial setting. And then I'm going to talk about algorithms in this framework that achieve stochastic-like guarantees while being able to handle these adversarial points. The second part, OK, the algorithms I'll give will not be super satisfying because this is a really hard problem. And we were able to come up with some algorithms. So I'll end with like a lot of open questions and maybe ask everybody to think about this problem and maybe come up with better algorithms than what we got. And please feel free to interrupt with any questions as I set up the model. OK, so let's start with defining the model. So this, I need to acknowledge Theodoros and Adam. I started working on this problem with them, but then we couldn't come up with an algorithm, so we decided to drop the project, and then I picked it up later with the other co-authors. So the model came from these discussions, so I have to acknowledge them. OK, so what is the sequential prediction problem? So here in the sequential prediction problem, I'm going to assume a very simplistic model where there is a there's going to be the true label that's going to be the prediction will come from some fixed function from a class that I'm going to call f, and I'm going to assume that that function is fixed, and so this is going to be the realizable setting with no noise. So it's a really simplistic setting, and what's going to happen is I'm going to get data x1 so on till xt, and each time the learning algorithm will be asked to make a prediction, it'll see the true label, then it's allowed to update its state, and then get the next sample, make its prediction, get the true label, and so on. And the goal will be, as standard in sequential prediction, you want to minimize this idea of regret or error, which is the total number of mistakes that the algorithm makes. And what kind of guarantee you want is that as you keep doing this for a really long time, the average number of mistakes eventually goes to 0. So you would want to eventually be able to predict really well. So you want this regret to be like little o of t. As t goes to infinity, that goes to 0. Okay, so now when you think about the stochastic setting, the assumption is that the data x1 to xt is all drawn IID from some distribution. And if that is true, then this regret guarantee depends only on the VC dimension of the function class. This complexity is like the same as the notion of offline learning, and basically, if the data is all stochastic, it's kind of like being in the offline setting, because there's no adversary trying to corrupt your data. Then you can also assume that the adversary, the data is entirely adversarial, so it has all kinds of dependencies. And in this setting, the regret depends on this notion called Littlestone dimension of the function class. And in fact, Littlestone dimension can be infinite even when VC dimension is 1. So this is not like a really good guarantee. It's pretty bad that you don't want to pay Littlestone dimension of your function class. And I'll talk about this example where Littlestone dimension is infinite, where VC dimension is 1. So the model that we propose is the following. So you assume that there is some unknown distribution D. Known or unknown, we'll make it clear. But there is some distribution that the data is coming from. And then what the adversary can do is that at every round, it can decide whether it wants to inject an example, an adversarial example. And it can inject that into the stream. So here, for example, x1 is from the stochastic distribution. x2, the adversary decided to inject an example. And the same sequential prediction task happens. So the sequence is stochastic, but the adversary can decide at each time if they want to inject an adversarial input. Just to make sense that there is a stochastic distribution, we don't allow the adversary to see the input before it injects. Because if it sees the input, it can corrupt the stochastic distribution underlying. Okay, now if you look at it for a little bit, the adversary could just corrupt the entire sequence. So it's not really like you're going to get anything out of this, because it can go from the completely stochastic to the completely adversarial. So we allow this extra power to the learner.
So here, when you say it's before the stochastic input is run, that's only for that round.
That round, yeah. So before the adversary has to decide that I'm going to corrupt this round, and then it decides whichever example it wants to put in, but it doesn't get to see the stochastic input that would have been in that round.
So would that make a difference?
Yeah, it could make a difference. So if you think about, like, if I know, if I see the stochastic input, I can choose to like cut out some part of the distribution as an adversary. So there's no notion of what the other sequence should like still look like stochastic, right? Otherwise, there's not much use of this distribution D. So if you think of it, like if I remove all the adversarial points, the sequence should be stochastic. And that's not going to be true if the adversary could see the point. So this is like kind of only injecting in the stream, you can think of.
And it's like nasty noise, so they can like corrupt both the...
No, so it's not corrupting the Y, it's only corrupting the X. You could imagine that the model could imagine corrupting the Y. So think of this as more like these adversarial example kind of setting where the actual true what the classifier is cannot be changed, but the adversary can add anything out of distribution to make us predict incorrectly. Yeah, that's a good point. So you could imagine extending this to both noise, but even just that is hard already. So it might be challenging to handle that.
And the level noise thing has been handled in this setting, in the sequential setting.
Which setting?
Just in this sequential setting, what is the, like, is level noise very, like just X is fine, but you just change adversarial.
Yeah, so it depends on how, so if your X is stochastic and you have adversarial noise, there are results for that setting. I guess here, the way I was thinking of this model was like we're only handling out of distribution in the data, input distribution, not in the labeling. Yeah, but good question. It would be great to extend it to that, but I think it'd be pretty challenging. Okay, so we allow this extra option of abstaining, which means that the learner gets to decide not only just 0 and 1, which is like positive or negative, but also can decide like I'm not going to make a prediction in this round. Okay, so now the learner can, in principle, if the learner could decide, know which points are adversarial and abstain, it could have performed really well. Okay, so this is the model that we're going to look at. You can ignore this. I'm just highlighting this as the model. And just a few points that we make assumptions here is that the model is realizable. That means there's a fixed F star at the start. You can handle adaptive F star in some cases, but not always. But what I mean by adaptive is that as long as the the adversary is consistent with everything so far, it can change what F is over time. That's adaptive.
So Surbhi, I guess I missed something on the last slide. So your goal is also to maintain the number of abstentions.
So I haven't told you the goal yet. Wait. Yeah, of course. If I abstain on everything, I'm done. But I will tell you the goal. Yeah. The other thing that I already mentioned is only insertion only. So the adversary is inserting an example before seeing the IID example. And of course, it extends to both. I'm not controlling how many points the adversary injects. Adversary could inject as many as they want. So it is the same as stochastic if no adversarial injections, and same as fully adversarial if all examples are injected. So now, of course, the question that Pravesh asked, that how can you do anything better? So we'll change the notion of what being good means here. Okay, so what do we want to do? We want to simultaneously minimize two quantities, incorrect predictions, which means whenever the learner actually decides to predict, we want to penalize the learner. The other thing we want to penalize is incorrect abstentions. So whenever the learner abstains on non-adversarial data, they should also be penalized because they should predict on IID data. So these are the two errors we care about. The misclassification error, this is just the mathematical notation of writing this down, and the abstention error, which is whenever the round is not corrupted, if the adversary abstains, if the learner abstains, it should be penalized. So one thing that you would notice here, if we just care about these two errors, that abstentions on adversarial examples are actually free. Question.
So does the adversary know the distribution? Like even if it doesn't know the sample?
Yeah, the adversary can choose the distribution.
So the adversary could, in every round, just put from the distribution?
Yeah, but then it's okay because I will not make too many errors on that. Right, which is actually a good point, maybe I write it here. Okay, it's on the next slide, but basically, I don't have to detect every example. I just have to not make mistakes. So I need to be sure that I'm predicting correctly. So that's why both the errors will balance that out. Okay, and the good part about this is because the abstentions on adversarial examples are actually free, we don't have to worry about how many adversarial injections there are because there's no factor of this C, the number of, usually all these models have this cost, C, the number of adversarial injected points. Here, because I'm not even paying for that, you can just cancel that out. If you're good, if your algorithm is good. Okay, so basically, as long as you predict with certainty, we should be fine with any number of adversarial injections. Okay, so why is it challenging? The adversary can, of course, add any number of adversarial injections. The learner does not know which examples in the history were injected. So the learner never gets this feedback that, okay, this was not an IID point. So it can't even compute its abstention loss. So it can only compute its misclassification loss. Okay, so the learner does not know which examples were bad. And the adversary could insert examples that maybe cause errors downstream. So there's like some dependency that the adversary could add. So we need to be kind of sure when we do predict, right? Like, so we want this certainty at every prediction that we make. And to point this out again, that we are not solving one example adversary detection. This will be very challenging. If every sample you have to predict whether it was out of distribution or not, would be extremely challenging. So as long as we can predict correctly on that example, we don't need to worry about it. Because it'll just go into the misclass. There'll be no error, basically. Okay, so this is, of course, connected to a lot of frameworks, and maybe some of you are already thinking of the connections. So there's been a lot of work on beyond worst case online learning. And this was mentioned before, there's like a setting of smooth adversary. So there you can, there are many ways to go beyond worst case. Here we are saying by giving the learner some power, but you can also block the adversary from having too much power. So the smooth setting, what it does is that if the adversary adds something, you perturb it by some distribution. So the adversary cannot give you like these worst case instances. So there's been some really interesting work in the last few years by Nika and Abhishek, who's also my co-author on this paper, on trying to get VC-like guarantees in the smooth adversary setting. There's also these other works that try to assume that the future sequences are somewhat predictable. So if the future sequences are somewhat predictable, then maybe you can deal with the adversary there. And this is like learning with hints. I might not be covering all the work in this sequence. Then there's also a lot of work on adversarially robust learning. So one, you can think that you have test time attacks, that your data distribution is clean, But then at test time, you can get adversarial points. And then there are training time attacks where the training data is corrupted itself. Okay, so here you can think of that in the online setting. You're doing test time and training time attacks because all the data that you've seen so far might also have adversarial points, and the data that you're going to predict on can also have some errors. But there's obviously a difference because you get to see the labels. The labels are still correct. There's been work on abstention-based learning. So in the batch setting, people have tried to use abstention to get faster rates of convergence. And I think the main paper that inspired this model is this transductive robust learning setting, where they assumed a similar model where you have, in the offline setting, you have a training data and a test distribution. The training data is all clean, and the test distribution might be corrupted, and you want to decide which part of the test distribution you want to predict on. And you want a similar kind of guarantee where all the things that you predict on, you get good results. You're making correct predictions, and you abstain on paths that you don't know.
Is this PQ learning model?
Yeah.
Okay.
PQ learning, yes. I think you can call it PQ learning. This one, I think the first paper just called it transductive robust learning. But after that, I think these guys started calling it PQ learning. And there's like a nice reduction of that to, I think, reliable learning. So you can connect that to reliable learning. Yeah, it makes it hard, yes. So this is the motivation, but we're thinking of the online version of this now, because at every point you have to decide. Not like you get this entire test set and decide based on that. The other models that, existed in this kind of knowledge, like know what it knows, is a really interesting model where you kind of, in the extreme case of our version, that you need to be correct every time you make a prediction. Here we are kind of trading off with the misclassification, and we're assuming there is a true distribution. They don't assume anything like that. And again, you can also get faster rates by abstaining here. And these are mostly either in the fully adversarial or purely stochastic. They don't try to interpolate between the two. And the last one that I find very interesting is this testable learning analog, which is, you can think of this as like some online version of testable learning, because testable learning is testing some assumption on the data, and you must succeed when that assumption is satisfied. And abstention you can think of as a tester that decides whether I should be predicting on this or not. And there are these two errors that they have, soundness and completeness, which kind of classifies to misclassification and abstention. So this can be thought of as testing whether your learner is actually a good learner in distribution. I guess Pravesh has a bunch of work on testable learning, so could see some connections here. Okay, so we haven't explored all the possible connections. There might be other related things, like I think with conformal prediction and other things also, these models are related.
Actually, because you mentioned testable learning, Adam and Kostas and Arsen have a new paper on testing distribution.
Yeah.
It's like a model of domain adaptation, which is in some sense also quite similar to, but some offline version of, I guess.
Yeah, it's like PQ learning, but there what happens is that you don't have to make predictions and decide where to abstain. You just decide not to predict entirely. Actually, we're working on extending that to the PQ learning setting with them. So it's kind of all related to how do you handle this kind of line of research that's how do you make this tester that actually adds to your learner so that whenever your distribution assumptions are actually true, you can predict well, and when they're not, you are sure that the learner will not output anything bad. Okay, so now that we have the framework and connection set, let's talk about algorithms. And I'll start with motivating it in simple instances to see why the problem is challenging, and then we'll come up to the main algorithm that we have. Okay, so let's consider this class, the simple class of linear thresholds. And this is the simple class where you have one parameter, A, and everything larger than A is labeled 1, and everything below A is labeled 0. So positive 1 I'll call it positive, and 0 negative in case I keep changing these. Okay, so this class has VC dimension 1, clearly, and the little stone dimension is actually infinite for this class. Okay, what's the challenge? So the adversary can choose a random A, and say you've seen these points and these labels. You know that this area is positive and this area is negative. So far, you've only seen this. What the adversary can do is it can choose to inject a random point between the closest seen positive and negative examples so far. And you as a learner would not really know how to predict this. And so the learner must predict. It will kind of make a mistake on this with probability half, and this would lead to T/2 mistakes over time if the adversary keeps doing that. But if you're allowed to abstain, there is a very simple thing that you could do if you wanted to abstain. What would that be? I could just abstain near the closest positive and negative. Okay, so the learner just decides that I'm going to abstain whenever I'm in between this window, and everywhere else I can predict correctly. So what happens here? You will never make a mistake. Why would you never make a mistake? Because whenever you're predicting, you're always predicting you're going to be sure, because you already know that point is positive, so everything behind that is going to be positive, and same with negative. And what happens to the abstention error? I only care about points that are IID, and I don't predict, right? So I only care about how many IID points actually fall into this window. And it's not too hard to see that after, if you've seen a bunch of IID examples, the probability that the next IID example is going to fall into this bucket scales as 1/t. Okay, this is like a simple exchangeability argument. So total abstentions is just like the sum over 1/t, going from t equal to 1 to capital T. This is like log t. So basically, like after you've seen enough ID points, it's very unlikely that they'll fall in between exactly the closest positive and negative. And if you add more adversarial points, this window will only shrink. Okay, so basically you get that this is 0, and this abstention error is just bounded by 2 log t. So here you, by just adding this abstention power, you went from paying this t over 2 to now paying in log t. So this is just like a proof of concept of like why this idea of abstention is useful. This is some technical thing that I kind of assumed that the adversary is non-oblivious, but you can handle an oblivious adversary. Sorry, I assumed it's an oblivious adversary, but you can handle a non-oblivious adversary. Don't worry about this too much, but this is the intuition. Okay, so then you could imagine, let me just go with this approach that whenever I'm uncertain, I just abstain. This is known as disagreement-based learning, where what you do is that you abstain on all points in the disagreement region. What does the disagreement region mean? Any point x where there are two predictors that are consistent with everything you've seen so far, but they disagree. This is exactly that window that was there in the threshold example. So you could imagine that I could just abstain on all of these points and then predict according to the consistent hypothesis. I will always get 0 misclassification error. And now it just depends on the quantity, like how many IID points fall into this disagreement region. And this is very well understood. And this is quantified by the star number of the hypothesis class. I'm not going to talk about what the star number is. It's not super important, but just to know that the star number is infinite for most hypothesis class of interest. So it can handle this threshold. The star number is 1, but the star number of anything more interesting is infinite again. So this is not going to work, and we kind of have to exploit. This is too strong. We're saying that there's 0 misclassification error. We need to make mistakes to learn. So this is not enough. Okay, so let's think about a slightly more involved class where the star number is infinite. This is the class of intervals. Okay, now instead of just having a single A, you have A and B. And you're positive only between A and B, and you're negative everywhere outside. Okay, so now what you can do, suppose the ID distribution actually has very low mass on the positive part. Okay, let's just assume that the ID distribution is of this following fashion, and it's only seen negative examples so far. So what's a disagreement-based strategy going to do? So if I get any point, since I've not seen any positive, that could be a positive, right? That interval, so everything is in the disagreement region. Right, so if I went by that strategy, I would basically predict, like not predict on any point. And that's bad because my ID distribution has like very low mass on positive, so I'm going to make a lot of mistakes on these abstentions on these IID points.
Wait a second. The
Yeah.
positive part has very low mass, right? So you will like, okay, so for the IID points that are in the negative part, you are actually making the correct prediction.
You're not making, right? Because what are you doing? You are predicting according to wherever I'm not sure. A disagreement base would be like, okay, I'm not sure about this point. It could have been a positive. It could have, because I don't know if that was the adversary's point or the actual distribution's point. Okay. Yeah, so every point, if I was just going by that disagreement style, maybe that's a bad algorithm. I'm just trying to motivate that that's a bad algorithm. So you would always just abstain. So you're being too careful, which is not a good idea, right? So however, it's better to predict negative everywhere. Because why is this better? Because, yeah, the learner can predict negative everywhere. So the strategy that the learner could do, this is just generalizing to negative and positive, that whenever any point is between two negatives or between two positives, just predict according to that style, that whatever that value is. And why is this helpful? This will not have, now misclassification error will not be 0, because it could be that that's a positive point. But the moment the algorithm makes a mistake, it learns the positive sample. And once it's learned the positive, it's reduced to now just worrying about 2 threshold problems. And then we can use the disagreement-based strategy now. So even though this did not make a mistake, the problem basically reduced to doing the threshold problem, which will only make log t abstentions, and at the cost of one mistake. So you paid one mistake and you do only log t abstentions. Okay, so make mistakes as long as they help with learning is a good strategy. So you should make mistakes if they're gonna improve your learning. And here you could think about like you started with the VC dimension 2 class, and by making this mistake, you went down to a VC1 class, 2 VC1 classes. So your mistake kind of helped you reduce the function complexity. So this is how the algorithm is actually motivated. It tries to do this. And this is the result that we have, which is not super satisfying because I'm going to make this really big assumption that I have access to the marginal distribution of D. And I'll talk about some results where you can handle without the marginal distribution. And so if you have access to the marginal distribution over the ID points, there exists an algorithm that for any class with VC dimension D achieves the following guarantee, that the misclassification error is D squared log T. This D square is an artifact of our poor analysis. And actually, Sham, he's a PhD student at MIT, saw this talk and figured out how to improve this to D. And it's a really clever trick, but I don't think he's written it down anywhere yet. So you can actually get this to be D log D, so tilde out D, which is almost the same as what you would get in the stochastic setting. And the abstention error scales as 6D. I mean, these are just constants. You can actually trade off these as you want, but you get basically ordered the stochastic kind of guarantee. And this works even if F star is adaptively chosen, as long as the realizability holds. And I think recently my student extended this to handle where you don't even get labels when you abstain. So you don't get access to the points label when you decide to abstain.
So the running time is not important here?
It is important, but we don't know how to do it computationally efficiently. I will put that as an open question. Yeah. Yeah, it's kind of going to use this idea, which I have already written up, higher order disagreement, and computing these higher order disagreements are very inefficient. Yeah. So, right. So it's like really just trying to show that this is even possible. Computationally would be a very interesting question too. We can do it in some special cases computationally efficiently, but like very special cases. I'll talk about this after. And on those special cases, you don't even need to assume the marginal distribution.
And is this tight? Or like, is there a sense in which this is tight?
I mean, you can't do better than D, right? I mean, if the entire sequence is stochastic, you'll pay this D log T. So I think it's tight in that sense, but I mean, this has an extra log D factor. But that might be also an artifact. Yeah, so I guess it's tight, but this is assuming the marginal distribution, which is very strong. So I don't know if you don't assume the marginal distribution, what's the guarantee that you get? And actually, the ones we get square root T. We don't get log T.
Also, what does access mean? Like, what does it mean that you can just draw?
Yeah, now you'll see in the next slide how strong the access is. So you can't do it with samples. Okay, so the key idea that is similar to what I motivated is that you want to predict in a way that mistakes will help you. And while ensuring that you're not gonna, so like you want basically like every mistake should get you some information. And as long as that's happening, there's only some limited amount of information to be gained because the function classes are bounded VC dimension. Okay, so what happened in the interval example was that whenever we predicted negative and made an error, we gained information to reduce the dimensionality of the problem in some sense. We went from VC dimension 2 to VC dimension 1. And that's kind of going to motivate this, where we're going to come up with like some algorithm that's going to tell us how well we are doing at different levels of complexity and try to go down the levels of complexity. Okay, so how do we do this? How do we estimate the dimensionality of our problem? We use this by doing this idea of shattering, which is what what VC dimension really means. So we compute this high-order disagreement-based shattering probability, which is that at every level k, you can define this idea of shattering probability, which is the probability that if I draw a random set of k points from my distribution, are they shattered by the function class or not? Okay, so if you think about this being k equal to 1, this is exactly the probability of the disagreement region. K equal to 2, 3, 4 becomes more complicated. So this basically kind of tells us that if I draw random points from my distribution, how much how much uncertainty I still have about the function class. Because if this is high, it could come from many different possible functions. But if this is low, then I'm probably sure that I am not at that level of complexity. And just to people who don't remember shattering is like a set of size k is shattered by a function class if all possible labelings are possible on that set. So there exists some f that can, there exists these f1 to all the Boolean hypercube f that can label them in all possible different ways. Some properties are very easy to see. That ρ1 is a disagreement region. Rho k is always greater than equal to rho k plus 1. And rho d plus 1 is 0 because d plus 1 points can't be shattered. So there's like an order of things that you already can see between these rows. So what is the algorithm? We start with the current level k equal to d because we are completely uncertain. We don't know where we are at. So we start at the top level. To make a prediction on x hat t, we compute the k shattering probability for the current version space with the restriction that x hat t is 0 or x hat t is 1. This should already sound familiar as a halving kind of algorithm. I ignore this quantity right now. So if both quantities are sort of large, we abstain. If both quantities are large, means this point is not very informative because it's not reducing my uncertainty either way. So I'm going to abstain. Else we predict according to the larger one. Okay, why predicting according to the larger one? Because if we make a mistake, we'll go to the smaller one. And if both quantities are pretty small, then we go down a level. Because we've already saturated that level, we can go down a level. And you can update the version space after you receive the label and continue doing this, right? Once you're at level 0, then you can just abstain at any point in the disagreement region and predict everywhere else, certainly. Okay, and the condition that we use is just like how much, basically this is kind of like the halving idea that if I take the rho k, the shattering probability of x going to 1 or x going to 0, the minimum should be greater than equal to 0.6 times what was already there before. This is just some arbitrary constant. But every time I'll reduce by this constant if I make a mistake. That's the idea. So it's kind of like doing halving with these uncertainty estimates. Okay, so I'm just going to give, I'll explain why IID points should not fall into this, why the low abstention, but it's very clear to see why you would not make too many mistakes, because each time you make a mistake, you're going to reduce by 0.6 at that level. You can only stay at that level for so many times, and there are only d levels. And the reason we get this d square because of our analysis is that we have to stay at each level at most d times, and we have d levels. But there's a better way to do this, that you can improve on all levels simultaneously to get like just d time. Okay, so the other thing that is left is like I'm abstaining every time the quantity is large, right? Why should I not be abstaining too much on IID points? And actually, there's a very simple, it's like literally just a Markov inequality that says that for any IID points, this probability of both being large cannot be true. Because IID points should be informative, right? So it cannot I cannot have so many IID points that keep coming that give me a high probability. And this scales as how certain I am of the level above it versus how certain I'm at my current level. And the intuition is the following. I'm going to give a very high level intuition. So you consider a set of k IID points. If they are shattered by both f of x going to 0 and f of x going to 1, then that means we have a set of k plus 1 IID points that are shattered. Right? So if each of these quantities was large, then this means that this quantity should be large. So if I know that I've already gone down to make this quantity really small, then it is not possible that I get both of these to be large for IID points. So this cannot happen too often if this rho k plus 1 is small. So this makes sure that I'm going down the level. I'm sure that if I'm at level k plus 1 level I shouldn't be. So I shouldn't be able to shatter too many k plus 1 points. So this allows me to basically say that IID points cannot pass this abstention test too frequently. Okay, so putting it together, we get a guarantee. The limitations, of course, lots of limitations, requires, now you can see how much marginal distribution access we need. You need access to computing the shattering probabilities. And I think I did not highlight this, but let me put this back. The threshold that we had to go down to was t to the minus k. So even estimating this would take a lot of samples. So it's actually not a great algorithm, even with sample access to the distribution. You really need to be able to compute shattering really precisely. And that's because this ratio you want to control and you want to control this really strongly, so you need to have these quantities be really small. So, and of course, so that means that to simulate this with unlabeled sample, we'd require this. Any naive implementation would require like t to the d samples, which is not great. And checking shattering can obviously be computationally very intensive. So for many function classes, computing shattering would be just not possible.
But even if you just had like, no corruptions, but if I only have the VC dimension bound, it's not easy to do it, right?
What do you mean?
Like how can I get, let's say, is it an efficient algorithm?
Oh no, yeah, you need an ARM oracle. Yeah. So I mean, you could imagine that I give you access to an ARM oracle, can you do this? But shattering oracle is way stronger. I mean, even if I use an ARM oracle, I would have to take all the possible labels and check whether the ARM succeeds or not. And that would be computationally and very intensive because I have to do all the possible k labels. So 2 to the k labels for the points that I have.
But you could sample.
You could sample. But I want t to the minus k kind of concentrations that I have to sample a lot.
I see.
Yeah.
K is only D, so you'll get 2 to the D.
2 to the d, yeah. No, I'm getting t to the d. Because I need to get to accuracy t to the minus k, the level. So, I mean, this is bad. You probably don't want to do this. Like, maybe, I mean, if I assume access to this shattering oracle or something. But yeah, it's a good question. Like, I don't know whether you can do something better. Maybe for half spaces, you can do something better. But yeah.
The D seems plausible, but yeah.
Yeah, so, but anyway, the thing was that it wasn't even clear you could get a VC dimension guarantee. So this just shows that you can get a VC dimension guarantee at least. So that's like a starter here.
So actually, because we made so many comments already, one more. In principle, you could expect to get something which is distribution dependent, right?
Mm-hmm.
Like VC dimension is somehow like a
Yeah,
bracket
this is
bound
worst
for all
case.
distributions. But perhaps you could say something in terms of like the distribution dependent Rademacher complexity.
Yeah, that's a good question. So I haven't thought too much, but I guess I could do a similar algorithm with like a Rademacher complexity instead of that and get something. But I need to improve. What notion of a complex? I'll have to figure out what thresholds I operate this on. Like how do I decide whether to predict or not? But I believe there should be a Rademacher complexity analog for the same algorithm.
So I think, but the nice thing is that you would only need an ARM oracle.
Yeah.
Because for computing, Rademacher complexity is like, I give random labels and I ask, what is the best fit error of an ERM. So in principle, you would be able to do that algorithm.
So you just need like an agnostic, like a solver for getting opt, right? Because the labels will not be
Oh yeah, we need agnostic.
We need agnostic. Yeah. So here we could, if we do shattering, we can go, we just have to see realizability or not. I guess, we still need an agnostic. Yeah, there might be a possibility to do this with Rademacher. Probably a better idea than doing VC, but we were just trying to get worst case.
No, but this is quite cool, yeah.
Yes. Wait, am I going in the wrong direction? Okay. So without access to the distribution, we can actually do some things, but very, very silly classes because we have to really use the structure of the problem. So for VC dimension 1, general VC dimension 1 classes, we can get the following bound. So you can get the misclassification and an abstention error to scale as square root t log t. So the error scales as square root t log t compared to log t in the known marginal case. So this is like way worse, but I'm not assuming any access to the marginal distribution. How this algorithm works, I'm not going to describe this one, but I'll describe the this other class that's much easier to describe. But we use this idea of, I think Scheib and David had a paper showing that every VC dimension 1 class can be thought of, you can take a tree structured orientation of all the points, and every VC1 class is like a path from the root for that. And that structure allows us to kind of decide when to predict and when to abstain. So we really use this structure. So it's not like we can get a very general purpose algorithm that's just text shattering. We can also do this for axis aligned rectangles in dimension D. So this is like a VC dimension D function class. And again, you get the square root dt log t compared to what you would have gotten would be d log t if you use the previous algorithm. So I mean, it's better dependence on d, I guess, but worse dependence on t. And I don't know if we can improve it. Kind of the trade-off, the algorithms that in these cases, what happens is that you get like some factor alpha and 1 over alpha here. And the only way to optimize it to pay the square root t. So I don't know if this is possible to improve. So or this is a barrier where if you
Not
don't
really
know.
better than D, right? Because T has to be at least D for
Yeah,
this
yeah,
to be.
yeah. There's otherwise it's not going to work. Yeah, yeah, it's not better. Also, like I don't know if this is a barrier, which would be interesting to see that if you don't know distribution marginals, maybe you can't do better than. But I don't know how to think about lower bounds in this setting, so that would be interesting to see. Okay, so let me explain the rectangle learner in the time that I have now. I went faster than I expected. So okay, let's think about this learning problem. So what is the rectangle problem? You have a bunch of points, and there is some rectangle that separates the negatives from the positives. So I'm assuming that one of the sides is zero-centered for ease. So it's just like a d-dimensional. So I need to just know one threshold here and one threshold there. That governs this. So what we do is we start with this, we just take our set that we actually know really well to predict on, right? So we know that if we take the smallest rectangle that contains all the positives, it should be positive inside this. And we can take the largest rectangle that excludes all the negatives, then outside that the label should be negative. So this is our certainty part. This is the area where we don't really know how to predict. Okay, so now we get a point in this. To make a prediction, what do we do? If xt is not in the disagreement region, if it's not here, we can just predict correctly because we will not make any mistakes. Else we do something interesting. So what we do is that we take this point and then we think about this problem as like just project it down to just this direction and project it down to that direction and see how many points are saying, it becomes like a threshold problem, right, when we put it down in one dimension. So now this point is like right next to the negative point, right? So this direction would vote that this point should be negative. And this direction would vote that this point is negative. So this point is like kind of like a certificate that this should be negative. So what we do is we count all of these. How many points are saying that this label should be negative if we've only cared about the threshold in that direction. So this is the votes to predict. So these 2 points will be witnesses to say that this is negative in the different directions. And if such number of points is greater than alpha, then we predict negative, else we abstain. Okay, so why would this intuitively work? So these are all the points that are saying that we are a witness for this point being negative. So if we actually predicting negative and it turned out to be positive, these points will be eliminated. So they can never vote for anything again. So we're going to make some improvement on, like, in the past, we'll cut down these alpha points whenever we make a mistake. Okay, so this is what's going to happen. So each time we're going to make this alpha, and what you can argue is that because these points are IID on each direction, because it's separable, again, that same exchangeability argument would say that I cannot be between negative points too many times. So I cannot be like certifying, if I'm an ID point, not too many things could certify me as a negative. So we basically get that we make no mistakes on positive points. Every time we make a mistake on negative, we eliminate one direction each of alpha number of examples. So you get this misclassification error as 2t over alpha. And the adversary can fool us on IDs as samples with probability at most 2 alpha plus 1 over n, that n thing is like the same 1 over t kind of thing, if you've seen an ID sample. So you get this kind of an abstention error. And then when you find the best alpha, you get that this alpha is square root t. And for this latter, again, we come up with this notion of attackability, which is that if the adversary knew all the ID points, how much can it attack an adversary point? And in general, both the algorithms kind of account for how much attackability is possible. It's a very strong notion because it assumes that the adversary knows everything and then how much it can attack. And we can show that it can't attack too many points. Okay, so this kind of is an idea of how we do this. Is like really exploiting the structure that all the directions are kind of separable, but in a general VC class, I don't think we can do this very easily. So you could imagine you could do it for some certain classes that have this structure. So the general class that expands this rectangles would be like intersection closed classes, but I don't know whether I can do it yet for intersection closed classes. But yeah. So I'm going to end with like a bunch of open questions. So how do you do this for general VC classes without distribution access? We only know special classes which really exploit the structure of the function that we have. A natural thing that you could imagine is that you could do, for the shattering, you could do a leave k out estimator if you don't have the distribution. So you drop k points and try to estimate whether those k points are shattered or not. And if you can make a robust version of this, then maybe you can use the history to maybe predict if you don't have the distribution access, but you need it to be robust to adversarial corruptions. There can be any number of adversarial corruptions. So this seems like challenging. Beyond realizability, noise models, like if you want random classification or other kind of noise models, I think we can handle random classification. But if you have other kinds of noise models, we really heavily use this realizability assumption when we go down or improve our function. So can we handle some better noise models here? And of course, this is binary classification. You can imagine multi-class, partial concept class. I think the more interesting one would be regression. How do you do this for regression? You could have a corresponding error that you only care about whenever you predict. You want to be close to the squared loss of the actual prediction, and when you're abstaining, you don't pay. How do you do that? Then, of course, computational efficiency is there. Are there efficient algorithms, or there is like a trade-off if you want efficient algorithms? I mean, there could be a trade-off even in knowing the distribution or not knowing the distribution, but this would be good to figure out. And then connections to other possible problems and techniques. So testable learning, conformal prediction. And I mentioned this SOS style robustness because SOS programs kind of have these indicators of which points are corrupted. Maybe there's some way to use these indicators to decide which points to predict on or not. So if we can do a robust estimation from our data that we've seen so far, maybe we can get some estimates to predict. And with I think Arsen and Costas, we are trying to do some SOS style algorithm to do. Maybe I can't say that we have gotten anywhere yet, but maybe there's some like SOS techniques that can help to extend this. And I think that's all I have. Sorry, I stopped projecting this. But yeah, I can take any questions. Thank you.